We have been differentiating for quite a while now, where we have y as the subject. We've been doing that for the last couple of years. And we've seen quite recently how we can differentiate if we have x as the subject and still end up with our gradient function dy by dx. Implicit differentiation is a technique that we can use where we need to differentiate where it's very difficult to have x or y as the subject at the beginning. So something like this. I've got the 2x cubed plus y squared plus 5x is equal to y cubed. Very difficult to make y the subject here. Very difficult to make x the subject here. So our previous techniques won't work here. We need a new technique, and that's implicit differentiation. So what we're going to do, we are going to differentiate everything with respect to x. So I'm differentiating everything on the left-hand side with respect to x, and I'm going to differentiate the right-hand side with respect to x as well. Now, the x terms will differentiate easily with respect to x. So the 2x cubed will differentiate to be 6x squared. However, the y terms, they are not going to differentiate with respect to x easily because they're y's. So what we have to do is use the chain rule. If I want to differentiate something with respect to x, what I could do is I could differentiate with respect to y instead, as long as I multiply by dy by dx. Hopefully you can see here from the chain rule that the dy here and the dy here chain together, and we get the d by dx, the d by dx. So we are allowed to differentiate with respect to y as long as we multiply by dy by dx. So, as an example, if I'm differentiating y cubed with respect to x, I'll differentiate it with respect to y, which would be 3y squared, and then I'll multiply it by dy by dx. So, just to repeat, if I want to differentiate a y term with respect to x, I can differentiate it with respect to y and then multiply it by dy by dx. So now we know that, let's come back to this example. And that y term, we're going to differentiate the y squared. So we're going to differentiate that with respect to y, which would be 2y, and then we'll times it by dy by dx. The 5x, that's going to differentiate easily with respect to x, that's going to be 5. And then on the right-hand side over here, the y cubed, if I differentiate that with respect to y first, and then I'll times by the dy by dx. And there we go. I have differentiated both sides of this expression, this equation, with respect to x. Now, usually when we differentiate, we end up with dy by dx as the subject. So that's what I'm going to rearrange for now. I'm going to rearrange to make the dy by dx the subject. So I'm going to subtract the 2y dy by dx from both sides. So on the left-hand side, I've still got the 6x squared plus 5. And on the right-hand side, I've got the 3y squared dy by dx minus the 2y dy by dx. Then going to do a little bit of factorising. So I'm going to factorise that dy by dx out from here and here. And then we're going to divide by those y terms to make dy by dx the subject. And there we go, we have got our gradient function, having differentiated implicitly. Let's do another example. So we're going to differentiate both sides with respect to x. So notice your first step here, it's like I'm doing, is I'm writing d by dx, which is the operator for saying I'm going to differentiate with respect to x, and I'm putting brackets around everything on both sides. Note that we don't just start by saying dy by dx like we previously might have done. We'll end up with that, we don't start with it. Right, differentiating the x squared. Well, that's going to be nice and simple because it's a x term, so that's going to give me 2x. The y squared, need to be a little bit careful with this because this is a y function, so we'll differentiate with respect to y, and then we'll times by dy by dx. Next, we've got this 4xy. Now we need to be very careful with this because this is a product of two functions. We've got the 4x and we've got the y. So we need to use the product rule to differentiate this. So if I say that u is 4x, and I'll say that v is the y. So differentiating the 4x, I get 4. Differentiating the y, well, if I differentiate it with respect to y, I get 1, and then I times by the dy by dx. And the 1 times the dy by dx will just be dy by dx. Applying the product rule now then, so I've got the 4 times the y plus the 4x times the dy by dx. And there we go. So be really careful with the product rule. Next we've got the 27. Well, when I differentiate 27, it will just become 0. And on the right hand side, differentiating 0 will also just be 0. Next, we're going to make the dy by dx the subject. So I'm going to, first of all, I'm going to subtract the 2x and the 4y from both sides. I'm then going to factorise out the dy by dx. And then dividing both sides to make dy by dx the subject. And the only other thing I might do is I notice that I can divide everything on the top and the bottom here by 2. So we'll just simplify that fraction. And we'll end up with minus x minus 2y over y plus 2x. Or I could just swap those terms around on the bottom. I could say 2x plus y, just so it's in alphabetical order. You don't have to, you could leave it like that. It's entirely up to you. And there we go, we've got the gradient function. So just to recap. Differentiating y terms, make sure you multiply by the dy by dx, and do be super careful with products. Now, given that we have now got our gradient function, This is what we just found on the previous page. Once we have our gradient function, we can do the usual things that we've done with our gradient function. So for example, I could be asked to work out the equation of the tangent when x is 2, which would roughly look something like this. I could work out the equation of that tangent by, first of all, substituting 2 into the original equation so that I can work out what the y-coordinate is at that point. Then substituting that into my gradient function. And then I'll have the gradient and I can do y equals mx plus c. So we can work out the equations of tangents or normals and do those sorts of things. We could also be asked these two questions. So I could be asked, where is the tangent parallel to the x-axis? So the tangent, the straight line touching the curve being parallel to the x-axis might be there or there. So I could be asked to work out these points here. Now, the gradient of these lines is 0. So I would make my gradient function equal to 0. Other ways of thinking about that, those are stationary points also. So we're used to dealing with those. As I move along that tangent, the change in y is 0. And so hopefully it makes sense that the numerator here would equal 0. What about if I wanted to find where the tangent was parallel to the y-axis instead? So let me mark that on, and we'll talk through that. So, tangent being parallel to the y-axis might look like here or here. Those are the straight lines touching the curve that are parallel to the y-axis. So I'd be looking to work out these coordinates here and here. Well, because those lines are vertical, the gradient is undefined there. Where do we get undefined values? Well, it's where we divide by 0, where our denominator is equal to 0. Another way of thinking about that is if I were to move along that tangent, or the other tangent, the change in x is 0, because I'm just moving up or down in the y direction. I'm not moving across at all. So the change in x is equal to 0. And so hopefully it makes sense in that way as well, why the denominator would be equal to 0. So having explained that, let's see the working out for finding those coordinates. So here is working out where the tangent is parallel to the x-axis, or the stationary points. You can see that I have taken the numerator and made that equal to 0. That's what I've got here. Which is then, I've made x the subject and found that x needs to be minus 2 times y. I've then substituted that back into the original equation. So I'm doing simultaneous equations. So I've substituted minus 2y here and here. And then I've just gone through the steps of solving that equation and found that either y is 3 or minus 3, which I've then plugged back into that equation to work out the x coordinates. So I found that I've got the coordinates minus 6, 3 here, or 6 minus 3 here. So those are the two coordinates, the two stationary points, or the 2 points where the tangent is parallel to the x-axis. If instead I wanted to find where the tangent was parallel to the y-axis, here I'm looking to see when the denominator would be equal to 0. Because, like I said before, these vertical lines, the gradient is undefined, or the change in x is equal to 0. So I've taken my denominator, made it equal to 0, made y the subject, and then done simultaneous equations again here. So plugging the minus 2x here and here, and then working through to solve that equation. I found that either x is 3 or minus 3, and then plugging those back into here to work out the y coordinates. So I've found that this point here was the coordinate minus 3, 6. And this coordinate here was 3, minus 6. So if we want the tangent being parallel to the y-axis, then the denominator is equal to 0.